home to check in around the same time as class time, and you'll see me teaching the class. So while you're at home, if this works, which I don't think it will, but we're trying, okay? I'll try for 20 minutes and then see how long it takes to upload, and if the 20-minute class works, then I'll try to upload the whole class so you can watch it at the same time as I'm delivering the class tomorrow when you're home. And then you can also watch the recorded version of it, because it's going to record. I'll have a copy of the class, and then I'll upload it to Google. So in case you missed something or if you want to review. Right. So the question is, what is the mass of a ball of iron 2 meters in diameter, given that iron has a density of 7.85 grams per centimeter cubed? Give your answer in tons. So this problem combines all the things I've taught you so far. There's going to be some exponents in there if we want. There's some conversion factors. There's the density formula, and there is rearranging the formula. So we're going to put all those skills together, and I'll show you what it looks like when you get good at it. All right, so the first thing we're going to do is convert the diameter of the ball into centimeters, because we're going to work with grams and centimeters. So we have a 2-meter ball times 100 centimeters per meter, means the diameter of that ball is actually 200 centimeters. Meters will cancel. Which means its radius is what? If the diameter is 200, what's the radius? It's always 1/2, right? Half the diameter is the radius, so the radius equals 100 centimeters. So now we have the conditions whereby we can calculate the volume of that ball. Remember that the density of anything is given by the mass over the volume. I've already given you 2 of those now, or I've already given you this one, right? I've given you the density of iron, but to find the volume, you have to do this calculation. That's what we're going to do next. And then once we have this and this, we can figure out this. So let's find the volume. The volume of a sphere is equal to 4/3 pi r cubed, where r is the radius, in this case 100 centimeters. So we'll plug that in. 4/3 pi times 100 centimeters raised to the power of 3. You're going to do that with a calculator. All right, so 100 second function x to the power of 3. Oh, if only I had my glasses, my kingdom for glasses, times pi times 4 divided by 3. And what you get is 4,188,790.20 centimeters cubed. Seems like a kind of large number, but it is a ball 2 meters high. That's a pretty big ball of steel, and I imagine it's going to be quite heavy. I estimate it's going to be in the order of about 25 tons. I find it hard to believe. Holy moly. Okay, we'll see. Anyway, density equals mass over volume. Now we know the density is 7.85 grams per centimeter cubed. We know the volume because we just calculated it. So we want to solve for mass. We can rearrange this equation by multiplying by v on both sides. That causes the v here to cancel, and then we get, after simplification, the mass is equal to the volume times the density. So let's put in the volume, which we just calculated, 4,188,790.20 centimeters cubed, and we'll multiply that by the density of iron, which is 7.85 grams per centimeter cubed. It may interest you to know that iron is a waste product of nuclear fission. Where does he? Okay, you can sit over there for today. Yep, right at the corner there. You got 2 papers for you. And your name is? Oh, KK. Right. like I was saying, it may surprise you to know that iron is actually a waste product of nuclear fusion. No harm done though. Resume, sorry for the interruption. Continue. That's an advance, they didn't have that a couple months ago. Okay. So we've established that the sphere has a volume of 4.18 million centimeters. Now we're calculating what its mass is. What's its mass going to come out in? When I cancel the stuff, it cancels. What's the mass going to be in? Come on, guys, it's staring you right in the face. What is that? What is that unit that's left over? Grams. So our answer is going to be in grams. So let's find out what it is. How much does this ball of iron weigh? Times 7.85. And what you get is 32,882,000 and 3.1 grams. Now, I said give your answer in tons, and I gave you a couple conversion factors to help you do that, to calculate that. So what we're going to do is we're going to say times 1 kilogram per 1,000 grams. You notice I put grams on the bottom here so that it cancels grams. And I'm going to say 1 ton, metric ton that is, 1,000 kilograms is a metric ton, per 1,000 kilograms. So basically I'm dividing by 1,000,000. And what you get is, how many sig figs? We're not 3, because this is 3 sig figs. So the answer you get finally is 32.9 tons. So a ball of iron 2 meters high would weigh almost 33 tons. That's like about 4 cement trucks. Yeah. Like I was saying, iron is a byproduct of fusion. So when a star is at the end of its life, it actually starts to turn the elements that it's fusing into iron. But once fusion gets to the point of producing iron, the nuclear furnace collapses. It stops producing energy. So the star begins to collapse inwardly, and then it collapses so fast that it actually bounces out again when it reaches maximum compression, and it creates a gigantic explosion that scatters matter all over the cosmos. Basically, all the iron that you see on the Earth at some point was in the core of a star, burning at hundreds of millions of degrees Celsius, and then the star collapsed, and the explosion hurled all the iron, all those microscopes, the iron that you see in the microscopes, the iron handles on these drawers, the iron that's in this stool was at the core of a star at some point. Maybe, who knows, 4 or 5 billion years ago. No, it would have to be maybe 10 billion years ago, because then another solar system formed with the matter that was found in the gas cloud that made our solar system. And all that is wonderful to think about, but at no point should it ever convince you that God doesn't exist, because time is just another thing that God made, but he's not subject to it. So, do you think you would be able to solve a problem like this if I gave it following the same format? You think you'd be able to construct an answer if I gave you a problem with the same setup? Yes or no would suffice. No. No? You couldn't follow the exact same steps?
Like I could, but it'll take time.
Yeah, okay. What if we try and do one, except we change the metal into aluminum instead of iron? You think you could solve it? I'll set it up exactly the same way. And you see if you get an answer like mine. You guys have a calculator? You should get a scientific calculator, because we're going to be using them. And there's no way you can do this in your head. At least I can't. So you should invest in yourselves, guys. Get yourself something like this. You can buy them at Staples here. I'll show it on the video so you can see what I'm talking about. You always watch at minute 9 58, minute 10, you'll see the calculator on this video, okay? Okay. Why don't we try another one like this? It'll follow the exact same pattern. If you do it, if you try to put your mind through it, it'll start to make sense, all the different steps you have to do. What are you doing in each one of these steps? In this first line, you're finding diameter in centimeters. In this line, what are you doing here? What part are you figuring out here in the second line? What's the first letter in that line? The V. What's the V? The volume. Finding the volume. Okay, so in science, no matter how big a problem is, in science, you break it up into little pieces. When you get a pizza, you roll up the whole pizza and stuff it in your mouth like a crocodile would? Or you take a little bit, a little wedge, and you take one bite off the wedge. It's no different in solving a scientific problem. You gotta break it down into little pieces and then solve each little piece, and at the end you'll solve the whole problem, okay? It's always like that, always like that. No matter how big your problem is, you break it up into little pieces, and then you can solve it. And right now you look at this and go, oh my gosh, this looks like Chinese. I'll never be able to do it. Yes, you will be able to do it. You just have to learn how to break it into little pieces. That's what I'm here to teach you. I may succeed, I may not succeed. I don't want you to be freaked out by it just because you don't understand it the first time. We're not in elementary school anymore. I'm trying to bring your level up, and if you can get to that point, you're going to have a much easier time of university or college, because they assume a few things in university or college. You should know how to do basic calculations, and the more you know, it's always the better, right? What are we doing in this line? What's that function called? Where you take one of the letters and put it all by itself. There's a word for it. It's called isolating the variable. All right, you're isolating the variable. Because we're looking for the mass, right? So I want mass all by itself. So we're isolating the variable in this step. And then in the last step, we're plugging in the numbers. So we're using the formula. And then here we're converting the answer into the units that we wanted. Okay, so we do, in this problem, I put together all the different things I've been teaching you for the past 2 weeks. So I don't expect you to get it right away, but I do expect you to study and try to understand. It's not going to happen magically. You've got to actually put a little bit of time to read the material. And if you can do that, that's fantastic, because you're going to develop your brain. Do you think it's possible to raise your IQ by studying? Is it possible to become smarter from studying? I think so. Otherwise, what's the point? Now, you can be born with a very high intelligence, but if you never study, you're not going to be any use to anyone, because you're not going to know how to do stuff. You might be able to figure things out on your own more easily, and that's why geniuses are so helpful to society, because they look at things and they tend to figure things out by themselves. But we're not all geniuses, so that's why we study. We follow in the footsteps of others. If you want to become a cobbler and make shoes, you're not going to just start from scratch and start making shoes with nobody to help you. You'll go and work with somebody who makes shoes, and he'll teach you how to make shoes. Imagine if we had to learn how to make shoes from scratch every single time we went to make shoes. You always learn a trade from someone else, but this is no different. You got to learn your science from someone else, and then you pick up the skills, and then you become more confident, and then you can actually have a conversation with scientists and understand what people are talking about. Try this now. It's going to follow exactly the same format as this one, except I'm going to change the metal. what is the mass of a ball of aluminum three meters in diameter, given that aluminum has a density of 2.71, I think, 2.71 grams per centimeter cubed. Give your answer in tons. May interest you to know also that we say aluminum, the British add an extra I. So if you're living in the UK, you're going to see this, aluminium. They throw in an extra I. We just leave it out. So I'm not mispronouncing aluminum. That's the way Canadians and Americans pronounce it. The British like to add in that extra I. Things like that have happened in the past where a group of people wanted to name an element and then it was renamed into something else. For instance, the element niobium was once called columbium. So it was obviously a group of Freemasons who did that because they like to use the word Columbia. I don't know what the significance of the word is. But you know, Space Shuttle Columbia, for example, Washington D.C. District of Columbia. The word comes up, and I've noticed there are usually Freemasons involved. They tried to name an element, columbium, but then it didn't stick, and it's still called niobium. I remember reading through a trade journal, and they were saying columbium. I was like, what's that? I've never heard of that element. And I looked it up and finally figured out what was going on. All right, what's going to be the first step? What did we do in the first step over there? We're finding the diameter in terms of what? Centimeters. Okay, so we're going to say 3 meters times, the conversion factors are all here. I forgot to write them, but they're still here on this board, so you can use them still. There's 1 meter and 100 centimeters, so 3 meters times 100 centimeters per 1 meter gives you 300 centimeters. We found the diameter of a ball. If the diameter of a ball is 300 centimeters, what's the next step? Find the radius, because you're going to use it in the formula. So what's the radius if the diameter is 300? 150 centimeters, because 1/2 the diameter equals the radius. In which case, 300 over 2 gives you 150 centimeters. Okay, so you found your radius now in centimeters. The next thing is we're going to find the volume of the sphere. It's 4 over 3 pi r cubed. So we're going to plug in all the numbers now. 4 over 3 times pi times 150 centimeters raised to the power of 3. When I raised that bracket to the power of 3, why did I first of all put a bracket around 150 centimeters and then put a 3 outside? What am I trying to do? What is that saying? Okay, I'm using the radius 150, but what? Yeah, we already found the radius at 150, but when I raise something to the power of 3, what does it imply about that measurement? Is it a length? Is it an area? Or is it a volume? What has 3 dimensions? Length, area, or volume?
Area?
No. It's one higher. 3 dimensions is volume, right? When you find say the volume of a cube, what are you going to use? Length times width times height. That's 3 dimensions. If I want to find the area of this bench, I'm going to do length times width. That's only 2 dimensions. If I want to find the length of the bench, how many dimensions? How many times do I have to measure to find length? Just once, right? Okay, so think about it that way, and it'll help straighten it out in your mind. So now let's plug in the numbers into our calculator and see what we get. We're going to take 150, raise it to the power of 3. Then we'll multiply that by pi. Does it matter what order we multiply numbers in? Does it change the value? If I say 2 times 3 times 4, does it change from 4 times 3 times 2? No, it doesn't. Gives you the same answer. All right, so I get from doing this 14,137,166.9 centimeters cubed, because it's a volume. What's the next step? I've just done this line here, which is finding the volume of the big ball. That's 3 meters in diameter.
Isolating the variable.
Isolating the variable for the density formula. So we're going to say density equals mass over volume. Which one of these 3 things do we want to find out as the answer to our problem? Do we know the density of aluminum? Sure we do. It's right here. It was given. This part was given. Okay, so read the question because it gives you the information. The density is right there. It's given to us in the question. Do we know the mass? No, we don't. That's what we're looking for. Do we know the volume? Yes, we know the volume. We just did it in this line. That's the volume right here. Okay, so we know this, and we know this. What are we trying to find? If we know this one and this one, what's the only other one that we can find? The mass. So we're gonna rearrange this equation so we can find the mass, because we know these 2. So how do we isolate the variable? We'll multiply by whatever we want to get rid of on both sides. That gets rid of the v. So therefore, the mass is equal to the volume times the density. And we've got both of those numbers. The density is this, and the volume we just calculated. So we're going to plug it in now, 14,137,166.9 centimeters cubed times the density, 2.71 grams per centimeter cubed. Centimeters cubed cancel. And we're going to get the mass of this ball of aluminum in grams, and then we'll convert it to tons if we want. So times 2.71, and the ball weighs 38,311,722.4 grams.
I got 0.3.
You got 0.3? Yeah, maybe your calculator has fewer or more decimal places than mine. Anyway, it's not going to matter because when we report the answer, it's going to be cut off over here. All this other stuff's not going to show up. You just never round during the calculation. Okay, so we've got the weight in grams, and now we're going to convert it to tons. So we're going to multiply that number by 1 kilogram for every 1,000 grams, and that helps to cancel grams. Boom, gone. And the next thing is 1 ton per 1,000 kilograms. And that gets you to cancel kilograms. So the answer in tons will be 38.3 tons. So what's heavier? A 3-meter ball of aluminum or a 2-meter ball of iron? Look it over here. 2-meter ball of iron is 32.9 tons. And a 3-meter ball of aluminum is 38.3 tons. So it turns out the ball of aluminum is heavier, but it is also quite a lot larger. It's a whole meter higher. Okay. That's probably the toughest problem you'll ever get in this class. It's right at the limit of what I want to be able to teach you. I know it's hard, but if you practice it, it starts to make sense. It just takes a while to sink in. So don't be discouraged if you don't understand it right away, but continue to study and watch the videos that I recommend, and you'll see that you make progress. The next thing I wanted to do with you is to just review the scientific notation sheet that I gave you here. So that's pretty easy, I think. And then I think the first unit we're going to do is the chemistry unit for grade 9. See what, after this unit, oh, we have biology, so maybe we'll do the biology unit first. And then chemistry will come after that. Okay, let's finish this then. How comfortable would you feel doing this? Do you find this sheet easy or challenging? This you should find easy, I think. Okay, it's not hard. If you came into the class late, then you won't have seen the techniques, but it won't be too hard to catch up. Just watch the classes. I'll put the different numbers on there. We can go through them. First one is 625. The decimal is here. So what they're asking you to do there is to convert it into scientific notation. The trick I showed you with scientific notation is to take the decimal and move it so that there's only one number before the decimal and then the rest of the numbers after the decimal. So in this case, you'd have to put it between the 6 and the 2. So you're going to say 6.25. But when you move the decimal over 2 times, you make the number 100 times smaller. So how do you fix the problem? You multiply it by 100. That's what scientific notation is. You're just showing one digit number before the decimal and then adding a power of 10 to fix the value. So you still have the same value, you're just expressing it a different way. And the power of scientific notation, if you were here yesterday, you could see how you can even convert between huge numbers using powers of 10 because they're easy to keep track of. You don't even need a calculator. I did a whole bunch of calculations yesterday without a calculator using scientific notation, and that's why I'm taking the time to teach it to you, because it really does make you think more clearly in terms of mathematical calculations. The next question is 4,216. You'll notice they put a comma there between the 4 and the 2. That's not really, you're not really supposed to do that. You're not supposed to put a comma in numbers. That's kind of this must be a European, yeah. Of course, yes, just sign in and out. So 4,216, the decimal is actually right here, but we want to put it between the 4 and the 2. So it's going to look like this, 4.216. And you've jumped the decimal over 3 times, so you're going to put it times 10 to the power of 3. Number 3, 49,603. So you see in that handout, there's a comma between the 9 and the 6. Don't write the comma. It's not SI. It's not good SI practice. What do you normally do to show large numbers instead of putting a comma? No, if you just want to write out the whole number, and there's lots of zeros to write, what do? You space out. You make a little space. You write 3 zeros, space, 3 zeros, space, and so on. Don't write the commas because it can be confusing, and you end up getting. You might, because the difference between this and this, in some cases, can be small enough that it might just look like a smudge instead of a comma, and then you'll end up writing the wrong number. So 49,603. The decimal is here. We want to move it to there. So it's going to be 44.9603. And how many times did we jump that decimal place? 4 times. So we're going to say 4.9603 times 10 to the power of 4. Number 4. The number 25 can be rewritten as, if you move the decimal from here to there, 2.5 times 10 to the power of 1. It's fairly trivial. 5, 18,569. The decimal is here. Move it to there. You get 1.8569. and you've made 4 jumps, so it's 10 to the 4. Number 6, 836. Now, who did this already? Who had it? All right, good. Nice. If you understand it, then I'm happy. I prefer you to be bored than clueless. I can work with clueless too. It's just less satisfying. But the boring parts I can't apologize for, because you gotta learn this stuff, or else you'll never really be able to do science. 9.364, decimal is here, so you move it over to there, you get 9.364. You moved it 3 times, so it's 10 to the power 3. Number 8, you have 912. The decimal place is here, you want it between the 9 and the 1, so it becomes 9.12 times 10 to the power of 2. 9, the 32. You move the decimal from here to there, so it's only 1 jump, 3.2 times 10 to the power of 1. Number 10, 912. Oh, what I did is I did number 10 here. So I'll do number 8 here to make up for it. Number 8 is 34,121. Decimal place is here, we move it to there, it becomes 3.4121. And you moved it, how many times did you jump it? 4 times, so 10 to the power 4. I did 10 already, so now we're going to jump to 11. 7,350. The decimal is here, we want to move it to there, so 7.35, and it jumped 3 times, so it becomes times 10 to the power of 3. Number 12 is 4,874. The decimal place is here, we move it to there, it becomes 4.874 times 10 to the power of 3. You have 62,503. Move the decimal over 4 times, so you get 6.2503 times 10 to the power of 4. And the last one, number 14, you have 13,058. Move it over 4 times as well. You get 1.3058 times 10 to the power of 4. And that's done. Now let's read a little bit of chapter 1 from the textbook that I use in grade 12. I know that sounds scary, but in grade 12 you learn a good part of the textbook. In grade 9, I'll be happy if you'd learn chapter 1, because it's got the key scientific ideas in it. I really enjoy it when, okay, I'm gonna stop the recording there because this is gonna be textbook reading. And then if there's more to do, we'll, how do I stop it? Okay, press X. Yes.